Following this presentation, we have Sunny Park.
Hi everyone, my name is Sunny Park, and today I'll be talking about my project on the determination of acid-resistant commercial membranes for forward osmosis. In Canada, mining constitutes a large fraction of our economy, but did you know in 2018, Ontario's mineral extraction industry spent over $115 per cubic meter to treat over 2 million cubic meters worth of waste? Treating mining and metals processed effluent has been a continuous challenge that introduces the need for cheap yet effective treatment methods. The term treatment in this context refers to the separation of clean water from a concentrated low pH effluent containing dissolved ions such as arsenic or copper, for example. Current treatment methods aim to do three main things: minimize waste disposal costs, recycle water for subsequent process use, and reduce environmental impacts. In order to meet these objectives, there are various methods of treatment that are commonly used in industry, such as reverse osmosis or distillation, for example. However, recent developments in membrane technology have actually shown that the novel process of forward osmosis can be successfully utilized in this separation to achieve these objectives. So our lab will focus specifically on the applications of FO. Now, what is forward osmosis, you may ask? Is a spontaneous membrane process involving two streams: a feed stream, or effluent, and a concentrated draw stream. As the feed stream enters the system, it is separated from the draw by a semi-permeable membrane. As the feed stream travels through the system, the osmotic pressure gradient pulls the water selectively through the membrane from the low osmotic pressure solution to the high osmotic pressure solution. This results in the dilution of the concentrated draw solution and the concentration of the diluted feed solution. This diluted feed is disposed of as brine waste, and the diluted draw solution is sent to a secondary separation process where product water can be removed and the concentrated draw solution can be regenerated and reused in the process. Currently, low pH forward osmosis membranes are an unexplored area of membrane technology. Most FO membranes are made of cellulose acetate, which when exposed to low pH environments undergo degradation. This happens as a result of acid hydrolysis, which in very, very general terms, in this case, refers to the reaction between cellulose acetate and water in the presence of an acid. These degraded membranes, this happens via the replacement of these acetyl groups with these OH groups. And these degraded membranes have lower water fluxes and salt rejection, which consequently reduces the amount and rate at which these contaminants can be filtered, which decreases the productivity and process efficiency overall, causing major problems in industry. In order to avoid cellulose acetate membrane degradation, pretreatments are often used to neutralize the feed before it even enters the system. These pretreatments are essentially just the addition of a base to neutralize this acidic effluent. However, the major drawback of this method is the inefficient nature of the process. For example, the following photos were taken after magnesium oxide, our base, was added to our raw feed and precipitation occurred. This precipitation required multiple vacuum filtrations in order to remove, which of course requires both time and resources, proving it's not the most efficient possible solution. Consequently, the main goal of my project is the determination of forward osmosis candidates resistant to severe degradation without the pretreatment of these low pH feeds. So the selection process actually explored membranes beyond the field of FO, including reverse osmosis and nanofiltration, for example, because the FO commercial market yields very limited options as a newer and developing technology. And we, as our lab looks into these new applications, we want to focus on highlighting these new polymer formulations that would potentially excel in these FO applications. Now, at this point, you may be wondering, Sunny, how can RO and nanofiltration membranes be used in FO applications? They are different mechanisms. Well, you have to remember that both RO and nanofiltration do have osmotic pressure gradients present. It's just that the fact that the hydraulic pressure, this applied pressure, overpowers this osmotic pressure gradient as the predominant driving force. So as a result, when we remove this physical applied hydraulic pressure, we have osmotic the osmotic pressure gradient as the predominant driving force, which allows forward osmosis to occur. An additional point, they also have very similar membrane structures, as shown here, as both are usually asymmetric composite membranes. So consequently, with alterations to their operating conditions, RO and nanofiltrations do have the potential to be utilized in these FO applications. These candidates from differing fields and membrane processes will be analyzed on their ability to meet the following criteria: commercial availability of flat sheet modules, an operational pH of less than 3, and greater than 90% salt rejection. This ensures that we can purchase membranes for testing, and the membranes are suitable for our feed, which is usually an effluent around 1.68 to 2 pH, highly concentrated in salts, arsenic, magnesium, and a few other elements. Only with the meeting of this criteria can each candidate be selected. So the 4 membrane candidates mentioned have actually been selected from a pool of over 30 potential candidates for demonstrating promise in related FO applications with similar feed streams. These candidates can be summarized into this table here. And an additional point of consideration that we were looking at is arsenic rejection ability, as there is a certain amount of arsenic present in our feed stream. So our first candidate is the Dalfilm-Tec XLE. This low-pressure reverse osmosis membrane was selected for its strong ion rejection ability at a high total dissolved solid concentration. It has an operational pH of less than 3, so it meets our second criteria, and it has the added bonus of arsenic rejection ability. As it is from Dow, a major manufacturer, it is also commercially available, and as it meets all 3 points, can be selected as our first of the final candidates. Next up, we have the Porifera PFO 100. This is a newer FO membrane that is still under development, and it shows a lot of promise against deformation, against forces such as hydraulic pressure. But the major drawback of this membrane is the fact that it's very limited in terms of availability from manufacturers. As a result, it cannot meet the first point of commercial availability, and as it doesn't meet all 3 of our criteria, will not be selected, although it does meet the other 2 points. The next candidate we are looking at is the GEAK, which is another low-pressure reverse osmosis membrane. This membrane was specifically chosen for its exceptionally low operational pH, which immediately meets the second criteria point. It also demonstrates the salt rejection ability, and as GE is a major manufacturer of membranes, it is commercially available. So, as it meets the criteria, once again, can be selected as a final candidate. Now, our last candidate is a nanofiltration membrane, which is also from GE. It's important to recognize that nanofiltration membranes require additional consideration in terms of salt rejection ability. It's especially important because nanofiltration membranes generally have larger pores than that of RO and FO membranes. As a result, we need to ensure that these nanofiltration membranes have strong salt rejection ability to ensure that only water selectively travels through the membrane polymers. This membrane candidate does just that, as it reaches our minimal requirement for salt rejection at a relatively high total dissolved solid concentration. It has an operational pH within our range, and it has an additional bonus of strong ion rejection ability of various metals, including cobalt, nickel, manganese, and more. As I mentioned earlier, GE is a major manufacturer, so once again, it meets the commercial availability point. So, as it meets the criteria, can be selected as our final of the 4 candidates. Now, to conclude, 3 of the 4 candidates from our sample of membranes mentioned have been determined to have potential in low pH forward osmosis applications, but it's also very important to recognize that literature data provides limited information about membrane behavior under our specified water sample conditions. The next steps of this project naturally require experimentation to properly evaluate water separation efficiency and degradation trends. However, given the circumstances, the selective candidates do show the most promise in their field for success in low pH forward osmosis applications. Thank you. I'll now open the floor to questions.
Thank you, Sunny, for your presentation. We now ask if judges have any questions to unmute and ask. If any attendees have any questions, please feel free to type it in the chat as well. Mr. Chen?
Sorry. Yeah, Sunny, very nice presentation. I just have a question. Do you know what are the pore size or dimensional differences of the three filters?
Usually we can identify the nanofiltration as being in the nanometer range, whereas the others do lie in, oh sorry, the other do lie in like the microfiltration range depending on the size. So the reason we're looking at forward osmosis as a technology is it kind of bridges that gap. It has the range, a large range of pore sizes that it can, particle sizes that it can filter. So it kind of connects the gap between the sizes of the reverse osmosis versus nanofiltration versus distillation. But it does have low energy requirements. So it is within the nano to micro range. It depends more. It is very dependent on the manufacturer, however, so it does vary from model to model.
Okay, great, thank you.
Thank you, Sunny, and thank you to our judges for the questions.
Thank you.